neat.
Is that neat, or do you like that, or what? Pretty tricky.
Oh, I like that color.
You like that? Okay. Okay, watch this then.
Hey, neat.
Nice colors. If you like that, wait till you see the next part.
Wow.
Oh, that's pretty. Mom, let's get that. Gee, did you really do this? Yeah.
Computers are very much part of our lives these days. And yet, for many of us, there is still a certain mystery about the computer. How can a mere machine generate designs? Ask us questions. Doctor. This manager. This scientist. These students. These people will show us 4 basic ways to use computers. Dr. Derek Sampson uses the computer to save lives. His program finds one name out of 4,000 filed in a computer, patients who are waiting for kidney transplants.
Hello, Christina.
This college student, for example, Christina Rivera, she must come every other day to have her blood cleaned. For 3 hours, it is pumped through an artificial kidney which removes poisonous wastes.
Kidney transplant.
Then I want to know the percentages of survival if I do have one.
Without this machine, Christina would die. What she needs is a real human kidney, but she must wait until a kidney is found that matches her body. A human body usually rejects tissue from another body. So when a new kidney arrives, a high-speed search begins. Prepares a row of numbers showing the kidney's blood and tissue types.
Partial match.
A2, 23, B13, B2, 57.
Prior to the advent of the computer, we would spend many hours on the phone reading out tissue types, looking for suitable recipients. The result of that was many kidneys were wasted because we couldn't find a suitable recipient.
About a year ago, the doctors began working with computer specialists.
So I'm going to need you to help me determine exactly what you want this program to do. What I'm going to do here is write a rough flowchart of what we're going to need. Now, what would be your first priority?
Well, the first decision point is to look for a perfect match, and the question is, do all 4 antigens in the donor match all 4
Computer
antigens
planning begins by identifying the exact results you want. To get the results, the computer must go step by step. Some steps are decisions which can only have 2 possible answers.
The computer cannot generalize. It will only operate based on a yes or no answer, essentially on a question or a problem.
Now, the next decision is it a 3 antigen match? And if the answer is yes, print that patient out.
Okay.
Right. And if the answer is no, the next question is the patient a 2 antigen match?
Okay. Reject.
The plan showing all the steps is called a flow chart.
So that it'll meet here, and then we'll go to
From
next
this,
process.
the application designer will write the
Go to your
actual
office
program.
And, write up your program, and then it'll be done.
Today, Dr. Sampson can call from San Francisco and hook up with a computer 3,000 miles away in Virginia.
We will enter the tissue typing data into the computer and look around the whole of the United States and Canada for a suitable match.
He enters the blood and tissue numbers for the new kidney.
Search will take 45 seconds.
While the computer searches for the best patient, we can look at another kind of file search, which finds a product and its price. Each of these 20,000 market products has a code number, which is also shown as a pattern of lines. The line pattern is converted to an electrical pattern, which is sent to the computer's storage disk, where all the product codes are filed. From 20,000 items, the system finds the correct name and price in a fraction of a second. Quick display from a computer file is also vital to these traffic announcers.
Lanes at the 57 junction. 2 lanes are blocked. Stay right for your best time past this jam.
The announcer reads from a list showing the reports in order of importance.
Sherry, I've got a SIG alert.
A SIG alert is an urgent report.
The traffic is blocked at Broadway and Main due to an injury, accident, and brush fire.
91 eastbound, 2 left-hand lanes from the 605.
After the producer keys in the report, she must rate its importance. She selects Bulletin, and the computer automatically puts the SIG alert at the head of the list.
We have a SIG alert situation following a bad accident.
The computer is invaluable whenever time is short and files are long.
It would be virtually impossible to do this kind of matching without the help of a computer.
Okay, and we'll slide it down. Just you're doing fine. Just stay as you are.
Jerry Curtis uses the computer in a very different way to control other machines. A new car rolls off this assembly line every 60 seconds. One key to fast production is welding by...
This is the teach control used to program the robot. I'll now move it to cycle start. Once I've determined the position for a spot, when I press the program button, it goes into the computer's memory. This light indicates that. There's the first spot. I'll put these spots in while playing forward to this spot. Enter. 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 I'll replay backwards to make sure I got the spots. And I'll run it in automatic. When I'm all done, I can check the functions on the CRT, make sure I have the proper program in. Flow chart that demonstrates how this is done.
When he planned the work, Curtis put in a test to signal the computer which program to run. The test begins with an electric eye suspended above the car roofs. This device is automatically turned on when a full roof passes below. You can see the red on signal. From the electric eye, the signal goes to a computer which controls the entire line. The calculating power of the computer is used to make models by Dr. James Blinn. He programmed a model to help design the robot arm of a space vehicle. A model of an arm begins with one line.
This line is described mathematically in terms of numbers. One of the numbers controls the length of the line. By turning this knob, we can change that number to make the line shorter or longer. Another number controls the orientation of it. We change this knob, changes the angle that the line is rotated. Turning sideways, it's 90 degrees, and going directly upwards, it's 180 degrees.
Dr. Blin's program allows him to add more lines, each controlled by numbers, and to see how the lines work together.
We can pick it up and move it down to the bottom here, so that when we change this angle, it looks sort of like an elbow joint moving. And if we go back and change the angle for both of them, this angle here rotates both of them, so that's sort of like the arm moving at the shoulder joint.
So computer models use numbers to describe things. These are numbers from a different model, which was set up to save the El Segundo blue butterfly. Its last remaining home is this small field between an oil refinery and a parking lot. To survive, the butterfly needs a supply of its only food, the buckwheat flour, and it must escape from parasites. Dr. Richard Arnold is trying to keep the El Segundo blue and other endangered species alive. He must decide every year whether to plant more buckwheat. If the flowers are too few, the butterflies will starve. But if the flowers are too many, the butterflies will suddenly increase, kill off the plants, and attract swarms of parasites. To help decide, they keep a careful count of the numbers of butterflies and the numbers of flowers. But the field is so small and the butterflies so few that one wrong decision could be fatal. So Dr. Arnold found a way to try out decisions safely by making a mathematical model. From his field observations, he estimated how planting buckwheat would affect the butterflies and parasites from year to year. He put his estimates into a series of equations which make up his model. Then he programmed the computer to do the actual calculations using a programming language called BASIC. A programming language is a code containing control words such as print and input. Suppose Dr. Arnold wants to experiment with planting some new buckwheat. In seconds, the computer calculates a generation or a year of growth. It will then repeat the calculations for a second generation, and a third, on and on.
Want to try again? Okay.
Models similar to Dr. Arnold's help students understand life systems, such as fish finding food in a lake.
Do you want to eat it or chase it? Let's eat it. Okay, fish 4.
Since computer models are based on actual counts of real fish or real butterflies, and counts are sometimes wrong, computer results are sometimes wrong. As computer people say, garbage in, garbage out.
I'll have to check my field data on them.
And sort of computer models always depends on the input of human beings. Julie Chambers and Karen Wilsey use the computer as a creative tool. For several years, Julie and Karen have been programming in a language called Logo.
Okay, this is called a turtle, and what it does is it draws. So with
The command words in logo control the movements of a small triangle called a turtle.
push return. Okay, and you see, it makes a line because it went up 100 spaces. So you can.
We asked Julie and Karen to make the titles for this film. At about the same time, their workshop got a new piece of hardware.
And we'll have to install it now. It's called a sprite board. And to use it, we'll put it in the computer first, and then after having done that, instead of having one turtle, you'll have 30 turtles.
This circuit board would be the key to the titles.
Like this, and then we're ready to go.
New hardware allows you to do new things.
With the sprites in the computer now, we have like 30 turtles when before we only had one. And each of these sprites can have a different shape.
Is there a limited amount of shapes?
Not really, because there can be as many as you can
But you have to do.
define. You can tell the
To
computer
use the
how
new
to
board,
shape any of these
they
sprites.
needed to learn
All
new
of them are
command
one of them.
words.
Now, if we wanted to tell it to move, we have to tell it how fast to move, so we can use set speed. All right? We can also change its heading in a certain direction. So to do that, you can just type in set heading. And I'll check back with you in a little bit, okay?
Oh, that was neat.
Maybe we could use that in the titles.
Okay.
Make it like a whole bunch of them.
Yeah.
Okay, like
Different colors.
Yeah, or different like
What color you like the background? Green.
and then have them move a certain direction. I
Yeah.
guess like have them go diagonally or
Up and down.
yeah. Okay.
Okay.
Let's see.
After shaping some letters, Julie found a way to make them move.
Okay, I was fooling around with some letters, and I decided to use a program to make the letters move around. I told Sprite 0 to set a heading at 45, and then I was looking at some speeds, and I decided the speed to be 15. Then I ended it.
Can I see it?
Okay.
That is really neat.
Then they divided up the letters of the title words and continued programming.
Here we go.
Finally, they were ready to try one of the titles.
Oh, debugging time.
Well, here we go. Let's act like detectives.
To fix or debug a program, you list it. Then look for mistakes. Computers make creative work in offices much easier. A manager preparing a report can try out different arrangements until she finds a layout that best shows her ideas. She can easily change the wording without erasing. The computer handles the details, allowing her to do the thinking. In a similar fashion, computers allow artists such as David M. to design freely, without mixing paints or cleaning brushes. It is the easy and quick response of the computer which makes it an exciting creative tool. So people use computers to support creative work, to make calculations, as in models, to control other machines, and to store and quickly find information in files. A vast variety of applications. And yet, all computer uses develop in much the same way. They start with a strong need that people feel. They often require long study and preparation. Large projects are developed by teams of users and computer people working together. The project is outlined in a flow chart, which details every step, including yes or no tests where it can switch paths. The computer is directed by a program, a series of instructions moving one step at a time. The program is written in a language made up of code words, which control circuits inside the machine. Every program may have errors. And finally, wrong input gives wrong output. Garbage in, garbage out.